We're gonna make a giant 15-kilometer long space gun and we're gonna shoot stuff into space. To most people, that just sounds like, no, you're not. That's insane, right?
Look, well, I did the math. Like, I've got the physics. The team that designed the SR-71 wasn't an army, and it wasn't billions of dollars. They had a broad enough group of engineers with diverse talents and willingness to work really hard, and, magic happened. First thing you need for conviction is the idea that it might not be impossible.
My name is Jonathan. Welcome to South Park Commons. I am
privileged to be joined today by Nato Saichek, who is the co-founder and CTO of a company called Longshot Space, where they are building a space gun?
A space gun.
Is that the preferred term?
We're trying to lean away from the gun terminology.
Space cannon?
An accelerator. I don't know.
It's not as punchy as
hard.
space gun.
It's the world's largest potato cannon.
Okay, yeah. World's largest potato cannon. So to kind of start things off here, let me set the stage. Let's say it's sort of sometime early in the next decade, some remote part of the world. There is a, roughly 3-meter wide and 10 or 15 kilometer long potato cannon.
Yep.
That has a several 100-pound or kilo projectile in the chamber.
Yep.
Someone's hand is floating over a giant red button. Does the red button say, do you say launch or fire?
We usually say fire.
Oh,
yeah.
It's a space gun.
Yeah.
Someone hits that button. What happens?
So we do have a red button right now, even for the small tests. Like, it was important. It's an important characteristic. The first thing that happens is, so the projectile, you've got to basically, the projectile fills the circumference of the barrel, and along the length of the barrel are a series of pressure vessels that are fully charged with high pressure hydrogen. Somewhere in the neighborhood of, again, for a space launch system, it might be 1,000 PSI, something like that. And when you push the button, a burst disk gets ruptured on the first two pressure vessels, and those release high pressure hydrogen into the barrel behind the projectile. It starts moving, and then as it moves down the barrel, periodically down the length of the system, more pressure vessels are sort of distributed down the length of the barrel, and as the projectile passes each set of pressure vessels, more burst disks pop, more gas floods in and accelerates the projectile down the barrel, and that gets you up to a certain speed. That's a pretty traditional, that's a potato cannon. Like, that's a multi-injection potato cannon, but you're just pushing a projectile down a barrel with gas. From a physics perspective, you can only, if you think of a gas as like a collection of particles, those particles are moving at some speed, and that speed is governed basically by the composition and the temperature of that gas. So if it's hydrogen, it's sort of a proxy for that, the motion of those particles is the speed of sound in the fluid. So hydrogen has a speed of sound of 1,270 meters per second. That's room temperature hydrogen. What that means is that a shock wave in hydrogen travels through hydrogen at that speed. And so if you had a volume full of hydrogen and you moved one of the walls, the hydrogen is going to want to fill that void, and some of the molecules can travel a little bit faster than that speed of sound of the fluid, but less and less of them the faster you're going. So when you start moving away from this volume of hydrogen, the pressure that the projectile feels drops off pretty rapidly once you're faster than that speed of sound of the fluid. So you can get up to the neighborhood of twice the speed of sound just by pushing the projectile from behind. After that, you're down in the neighborhood of, like, if you had 1,000 PSI behind the projectile and the projectile's traveling at 2.5 kilometers per second, you're feeling something like less than 100 PSI. You're feeling less than 10% of the actual pressure in the gas. So what that means is all that energy that you put into the gas to pressurize it is basically being wasted at that point. And 2.5 kilometers per second is nowhere near the speed you need to go to space. 8.5 kilometers per second is sort of what we target for a space launch system, because we're going to need to punch through the atmosphere and get to orbital altitudes at orbital speeds. So orbital, the speed, typical speeds you're talking about is something like 7.5 kilometers per second. So we expect that we'll lose like a kilometer per second punching through the atmosphere. So we need to, leave the barrel at 8.5 kilometers per second so that we can get to orbit at 7.5. But I've only described how we get to 2.5. So that's just that's the easy part. That's the part that like we did sort of.
Yeah, there's a lineage to this. We'll get
Right,
to that
yeah, okay,
that part. So kind of that had been the big potato cannon had been
Right.
figured out.
Yeah.
You came up with a way to then get at that additional
Big
like
chunk.
kilometers per second.
Yeah.
And also presumably to like reduce the G-forces in such a way that like you're not going to just splatter whatever you put in the projectile. What does it sound like when it leaves the barrel?
Yeah. So we have a couple of systems that we have operational right now. One of them is a 6-inch diameter system that's 60 feet long. The other is a 30-inch diameter system that's 120 feet long. It's the largest cannon in the world right now. And we've only done one commissioning test shot. We're still in the process of bringing it up. We insulate the system a lot. Initially, we didn't insulate it a lot, and it sounded like a shotgun plus a car crash. But we've added a lot of insulation to the system, and now it sounds like somebody dropping a load of bricks or a shipping container, and there's a very visceral thud as you feel it in your chest, and the cuffs of your pants move a little bit. The volume of air that we're moving and the rapidity with which that is happening, like there's a shockwave, and the whole thing is anchored to the ground, and so the ground moves.
So it's really fun to hit the red button, is what you're saying.
It is.
Like that has to be the best part of everyone's day. Is like, you get to hit the red button.
It's an adrenaline shot. And we fired the 6-inch system. We fired more than 100 times. So we had a rule at one point where we made it so that it was the least senior person at the company had to push the button, so that we were trying to make it so that our CEO would never push the button. That was the goal.
Wait, hold on. Why? There are two ways you could interpret that. One is you're the red shirt, so you press it. The other is this is so he's not always just only like pressing the button. We need to get everyone involved.
Yeah, it was a way to keep everyone involved. It was also sort of an ambitious goal of like, we are gonna make so much progress so fast, we're gonna grow so fast that there will always be new people and he'll never get a chance to fire it. Unfortunately, he ended up, in I think it was in early 2025, he had to push the button. No one else. We didn't have anybody who we could invite over as a visitor or something, to push the button, unfortunately.
Okay, well, I volunteer.
Okay.
That is
That's
ever a
tribute.
problem again. All right, so there's like a history to this idea, right? Seems to go back at least to Jules Verne, right? 1865 novel,
And then,
around
yeah.
this exact concept, except putting people in it. That probably won't work.
Very similar, yeah.
Germans tried to turn it into a weapon in World War II. There was a project in the 60s called HARP.
Yep.
And there was a project in the 80s and the 90s called SHARP.
Right, Super HARP. Yeah.
Super HARP.
Yeah.
So I guess the question is, like, at each of those steps, people were conceptualizing it or testing various stages of it. What changed that made you think, oh, now actually we can go back to this particular idea that was abandoned at various points?
Yeah. Story with HARP is HARP worked. They were firing projectiles. Gerald Bull in the 60s and 70s was firing projectiles to orbital altitudes for $5,000 a shot. And he was getting CubeSat-sized masses to orbital altitudes. He had a whole system called a Martlet, which was a 3-stage solid rocket motor designed to put a CubeSat-sized object into low Earth orbit. The problem was, in the 60s and 70s, there was no such thing as a CubeSat. In fact, there was no such thing as a commercial space industry at all. No one at that point cared a lick for the marginal cost of space launch. The only thing space launch was good for at that point was either like massive national prestige projects where cost doesn't matter, or nuking somebody else, where again, if you're ending the Earth, it doesn't matter. The marginal cost of launch doesn't matter. We're gonna wipe all life out on the planet. How many times do we need to do that? I'm on a budget here. Like, nobody cares. So the idea that basically in the last, say, 15, 20 years,
SpaceX happens.
SpaceX
That's
happens.
a big part
Yeah,
of it.
a commercial, the idea that it is commercially viable to be operating stuff in space, and that cost per launch, cost per kilogram matters. And so if you were looking at the fundamental physics, like rockets are not the best way to get things into space cheap, but they are a portable way to move nukes around and be unblockable. So we invested cumulatively as a civilization, the US and the Russians, something like $4 trillion in rocket development. And so we as a society, plowed a lot of resources into developing this technology. And once you're in a local optimum there, it's really hard to get your way out of it. But basically, my co-founder Mike got a lot of conviction around it, and he yelled at me a lot, and we talked about it a lot and fought about it, and eventually we sort of hashed out our sort of like current architectural design. And we think that it is a plausible path to get, I don't know, he quotes $10 a kilogram, but I'm like he's the guy who keeps, he keeps our eyes on the sky, and I try and keep our feet on the ground. So I'll say, less than $100 a kilogram. Be a little bit more conservative. I think
what is the current cost for chemical rockets?
Falcon 9 is something like, if you want to go buy a Falcon 9, you'll pay, $5,000 or $7,000 a kilogram, and internally their costs are something like $3,000 a kilogram. When Starship is operational, they'll be charging something like $1,000 a kilogram, with internal costs less than that. But it's hard to say because it's not operational yet.
So you're targeting orders of magnitude reduction in costs.
At least one full order of magnitude better than that. That's the goal.
So the interesting thing about companies like this, and we've had a chance to work with a few recently at SBC, building kind of space tech or hard tech sorts of companies, is so often the mechanics of the company seem to, they're physics problems.
Yeah.
Right. More than, what is my go-to-market? What is my, right? It comes down to just literally, can you solve for the physics? And here it seems to be that if you can, in fact, accelerate something to that speed, right, to 8.7, whatever it is,
right,
kilometers per second, you can get something into orbit. And then from there, the question becomes, what are the sorts of things that you can do that to, such that they survive and are economically valuable in orbit?
Sure.
So it seems like a big part of the question here is around the G-forces, or the actual physical effect on objects. How do you think about that as an element? Because I know that's also part of the reason for the engineering here.
So in some ways, we're really fortunate that spin launch exists. They sort of pioneered the kinetic launch market segment, and at least they proved to some people that you can raise money doing a kinetic launch company, which made it possible for us.
Their version is a centrifuge, right?
Yeah, the sort of the difference is we invest the energy over distance, and they invest it over time. So they spin up the centrifuge over a couple of hours. Our shots, a full-scale system shot would take about 2 seconds to go down the length of the barrel, and then another 10, 15 seconds to transit the atmosphere, and you're in orbit in less than a minute. Oh yeah, so spin launch, they built a centrifuge, and they spun CubeSats up to 10,000 Gs and demonstrated that they work fine. And they demonstrated I think it's either a control moment gyro or a momentum wheel, basically a bit of kit that you put on a satellite that is used for orienting a satellite, and they spun that thing up on their centrifuge and demonstrated that it can handle 10,000 Gs. And so they sort of demonstrated it's totally possible to design and build hardware that handles, frankly, we think that's insane G loading. We're aiming to have our G loads be much, much less than that. If you take your cell phone and, I drop it onto the ground right there, that was 400 or 500 Gs that cell phone experienced right there. Just maybe not, this is sort of soft carpet, but if that was concrete, that'd be 500 Gs easy.
I admired the commitment to making the point. I assume you've done that before.
All the time. Yeah, no, your phones are really robust.
He's I've gone through 14 different phones.
It was a little bit risky. This is a relatively new phone and I don't have a case on it. But my old phone, I've done it. I can't even say how many times. But I would hold it 6 feet up and drop it onto concrete. Cell phones are pretty robust. They're designed to handle hundreds of Gs repeatedly. And the worst that often happens is your screen gets chipped, right? The electronics inside that thing, it's never the case that I dropped my phone and the CPU popped off the board or something, right? We're designing the system to keep the G loading less than 1,000 Gs. And so we think that basically at that G loading, the electronics will have no problem surviving. That's I would say, non-controversial. The things that would be challenging is if you've got, some geosat might have giant solar panel wings on it that extend out, the largest geosats, their wings extend out larger than a 747. So if you're gonna have these like colossal deployables that are weight optimized and, ephemeral things, like, yeah, those, you're probably gonna have to put some gussets on that, or like, make it out of steel instead of aluminum or something like that. But the thing is, if you have to bump up the mass of your mechanisms by 10 or 15%, and in exchange you can launch for an order of magnitude less.
It's a trade-off, right? Like if you are driving down the cost of launch, there is a marginal cost to make it launchable, right? Again, the economics become physics problems.
We have a dream that like if you wanted to do a moon lander, instead of like going and designing a moon lander, you take a John Deere tractor, rip out the gas motor, stick in an electric motor, and replace the rubber wheels with aluminum wheels or something, stick it in a shipping container and send it to the moon. Like, because that would be so much cheaper than like custom designing a specialized aluminum moon lander. Like no, when it's, $50 a kilogram, who cares? It's like twice as expensive to send it to space as it is to, send it to Europe. Who cares?
Well, presumably it's like use in environments like the moon is also one of the advantages here, right? Where you can do even more with this sort of a concept and probably drive down the cost even more.
Oh, if we put one of these things on the moon?
Yeah, I mean, is that something you're considering?
I think it's totally possible. There's a lot of oxygen on the moon. You have to bake the rocks to get it out. But the thing, we're a gas-based accelerator. So space is not notorious for being full of gas. But the moon would be reasonable because even with an oxygen-based accelerator, speed of sound of oxygen's in the neighborhood of 300 something meters per second. So we could easily go, a kilometer. Exit velocity from the moon is like a kilometer per second. So we could totally do something on the moon with oxygen. We don't need hydrogen on the moon.
Okay, so that kind of brings me to a topic, because I think you kind of just went through and sort of experienced it in real time there, which is one of the things I like about the Longshot story and the giant potato gun is it sounds a little bit like a high school science project. I mean that in the most complimentary sense, but then like taken to its logical conclusion. But there is a mindset behind that is sort of, I guess, like a beginner's or learner's mindset, which is to say it is a credulous and curious mindset instead of an incredulous, skeptical one.
Yeah.
And it seems like there's so many ideas where it's very easy for them to not happen because you describe it, you're like, we're gonna make a giant 15-kilometer long space gun and we're gonna shoot stuff into space. And like to most people, that just sounds like, no, you're not. That's insane, right? And then someone, like, if you are the type of person who can be like, let me do some math.
Right. What's the next step? What's the first thing I would need to figure out?
Which is true of like most founders, right? That is what founders do is they stop and they go, but wait, maybe it'll work, right? And then you convince a few people, but most people go like, no, you're not going to do that. But you experienced this with your co-founder. Yeah, I understand it, right?
Yes.
It's like originally your co-founder, my research suggested like saw some version of like a TED Talk from the guy who ran the Sharp program.
Yep. John
and I was like, well, this sounds cool. Why don't we try to do that again? And then was friends with you, called you up and said like, I want to build a giant space gun. And you went, so talk to me about that process.
I've got my feet firmly on the ground. Yeah. No, so I've known Mike for something like 15 years. I was an early employee at Planet. I was making Earth observation satellites. And that was originally in a garage in a house in Cupertino. And Mike lived in the house.
Classic.
Right. And so I was eating him out of house and home. I was eating his groceries from the fridge for lunch. And then eventually we became friends. And he has always had a lot of crazy ideas. He'd call me up and be like, hey, Nato, I want to build a solar-powered blimp that carries its own electrolysis machine so it can like land in the ocean and then refuel. And then, we talk about, we go back and forth like, oh, okay, I've got an idea. I want to make a retrovirus that like turns my eyes green. Like, okay, he's like all kinds of, he'd have a variety of ideas. And, I've done a little bit in biotech. I'm a multidisciplinary engineer. And so we'd go back and forth and sometimes we would play with stuff. We got a giant Fresnel lens and we'd bake stuff in my backyard or in the garage, or we built microwave susceptor materials for a microwave rocket thing that we were talking about. There's a whole bunch of, so we played around with a whole bunch of ideas. And when he came with the space gun idea, I basically oh, you got to align the barrel. That's going to be impossible. You got to do this. It's going to be impossible. This is hard. This is hard. This is hard. This is also, you're not even how are you going to do this? You can't prototype this. It's really hard to prototype this thing. It's a lot of these things you can think of. How do you make the first small thing, and what can you do in the garage scale? And we could come up with things, but this one seemed really hard to do any of that. But to his credit, he basically just kept coming back with, I talked to this professor so-and-so, and they showed me this paper where they did this, that, and the other, and we can solve that problem this way, and that's a good point, okay, da-da-da-da. We went back and forth, and eventually the last objection that I had was that the system was gonna have to be too long. It was gonna have to be hundreds of kilometers long because of this, this gas pressure drop-off thing or something. I don't remember what my reasoning was. And he said, I don't think it's going to be that bad because we've got this, that, and the other. And I was like, look, build a simulation, run it, and you'll see it's going to be too long. And he's like, I'm not a coder. I don't write simulation. You make a simulation. And I was like, okay, I'll make a simulation. So I made a simulation. And at first it came back really bad. And then I found, I flipped a sign there. Okay, fix that, oh, extra zero, get rid of that. And came back, okay, look, this thing only has to be, 4.5 kilometers long. And he was like, I think it needs to be longer than that. 4 kilometers long, there's no way we're gonna do it in 4 kilometers. So I'm like, look, well, I did the math. I've got the physics. Look at this. And he's like, I don't care about the physics. The main thing that just happened here is you believe the system more than I do now. So how come you're not on board already? And I was like, okay, good point.
I mean, what you've described is a kind of a classic, right, having both sides of something, which is, right, eye in the sky and feet on the ground,
yeah.
And sort of an iterative process of helping each other build conviction in the thing.
Yeah.
Because I have to imagine that he was thinking I have to be able to convince Nato.
Yeah, he needed to be able to convince technically competent people that this thing is plausible, or it's not going to be, no one's going to build it, right? But once he had me on board, I feel like it makes it a lot easier if you can say oh, here's a guy who's been, building satellites and rockets and robots for, 15, 20 years.
Yeah, because you were at a rocket company.
Yeah, I was at Astra.
You were building rockets.
I was integration lead. I was literally building rockets. I delivered an upper stage and then I delivered 2, full rockets. And that was my degree's in aerospace engineering. Building rockets has been my dream since I was a child. This was a dream come true that I'm getting to build rockets. And then Mike's like, now rockets are dumb, And it's like, oh, that's a good point. That was the other sort of side of things. Is it was a question of impact. And he basically said, if the company you're at right now is absolutely as successful as it can be, and you have the maximum impact you're going to have there, what's it going to be? And I was like, company has, 150, 200 people in it. If I have an outsized impact, maybe I have a 2% impact on the future of the company as just a generic employee. And if that company is massively successful, I'm not going to pretend that they were going to eat SpaceX's lunch. They're going to maybe have, an extra 1 or 2% up mass. 1 or 2% more stuff is going to go up and costs are going to come down for 1 or 2% customers, something like that. So I'll have a single-digit % impact on a single-digit % impact. For a human in the world, that is a colossal impact to have in general. But when you're given the opportunity to have a double-digit % impact on an order of magnitude impact, it's nothing, The opportunity to work on something like a space gun that could drop the cost by an order of magnitude, and that I might, as a co-founder have, hopefully I have a double-digit % chance on, or double-digit % impact on the, the success of the venture. That was, the only thing stopping me then was the American healthcare system. I needed healthcare. So Mike then got a phase 2 grant from the Air Force, got enough money in the bank that we could get healthcare, and I quit my job and joined up.
So you were doing it sort of just an internal expected value calculation.
Yeah.
I want to kind of take that and go back a little bit to something you mentioned before, which is the way that you go about kind of getting stages of proof and sort of adjusting the way other people, yourselves, think about that expected value calculation. It's different for hard tech and for something like aerospace or space gun, whatever, kinetic aerospace, than it is for traditional software, right? And very often, I mean, almost always, there's just going to be a much longer product development cycle before you reach any kind of version that works at all, or that proves or like secures a contract, or you have customers for.
Yeah, it's tough. There are counterexamples. The first nuclear, I think it was like the first nuclear submarine was built in like a year. Like there are kind of crazy examples.
Your counterexamples involve the Cold War and like
right,
like the most powerful nations on Earth.
But the Skunk Works is 50 engineers. You know, the team that designed the SR-71 was not, that wasn't an army, and it wasn't billions of dollars. It was tens of millions of dollars and less than 100 engineers. And I can't say I can do that. I hope I can do that. I've read books about engineering management and stuff. But you need deep engineering experience to do those things. Those people had already designed and built dozens of airplanes beforehand. They had already built all kinds of. Everybody involved in those systems had a deep technical background in those domains. They had done similar things before, but they'd never done like that first thing, that amazing thing had not been done before, but they had a broad enough group of engineers with diverse talents and willingness to work really hard. They put them together, managed them well, gave them good goals, and magic happened. I can't say that. I'm sure there've been the picture of the airplane with all the little red dots on it. We're looking at the project that succeeded, not the ones that failed. But it's a sort of a, and this is maybe getting to the same thing you're talking about. It's an existence proof. The first thing you need for technical, for conviction, is the idea that it might not be impossible. It has to be not impossible. And if you can show that it's not impossible, like, okay, you're never going to raise money for it. Okay, well, that's an argument, but like, if it's
it's not impossible.
Right, but yeah, exactly. There was a project I was working on once where we were working on designing a solar sailing CubeSat that the goal was to solar sail to the moon. And we were, I was just with a group of friends and we were in a garage. Somebody was worried about like, how are we going to get funding for this? And one of the people who was working on it basically said like, funding is negotiable, solar pressure is not. Like the amount of sunlight that we're going to get is not a negotiable thing. We can't argue that away. We have to solve this problem about the size of the solar sail. If we have to make it twice as big and we have to ask for twice as much money, okay, then that's what we'll have to do. But first we have to solve the physics, and then we can worry about the money.
So you just did a ton of like very compelling storytelling. This is something I spent a lot of time on with the members and founders here at SBC, and in particular, a lot of the people who are doing kind of more deeply technical things, because you just have to get people to believe, to suspend their disbelief for a longer period of time, and often to a greater degree because of the capital costs. Yeah. The physics are non-negotiable, but then you can tell a story once it's like, it's not impossible.
Right.
How did you and your co-founder approach that process early on as you were going out and like convincing your first investors to join, or like as you were trying to expand the circle of people? Obviously, Mike had already gone and gotten a grant for the project from the government, but then you needed more capital, and you had to start convincing more and more people to kind of join the vision.
Yeah.
Was that an iterative process, or was it mostly just like space gun and like whoever vibed with that?
So I think we actually overestimated the amount that early investors would care about like technical diligence. Once we had a physical thing that we had built, we demonstrated we have a team here, we can build stuff. We had a Air Force grant, so we were able to convince somebody that this thing was not completely useless. Mike, can tell this part of the story way better than I can, because he was the one making the phone calls, and if somebody had technical questions, then he would drag me in. But that was almost never. He would call and get kicked in the teeth for hours, for weeks, hundreds of calls to potential investors. Either they didn't care about space launch, they only cared about short-term weapon applications for blah, 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 or they didn't care about weapon applications, they only cared about space launch, and then we're a tiny little company in a garage. We don't have, how long is it going to take us to build a space launch? Well, it's going to be more than 4 years, and that's the horizon over their investment horizon, so forget about it. So he got kicked in the teeth repeatedly by tons of investors for a whole bunch of reasons. Almost never, I think there's maybe one investor who, like, we couldn't, they were going to invest, but we didn't give them the enough technical credibility. I think mainly if an investor would come over and they would see, we have the team here, they're working hard, there's people out there, they're cutting metal, they're grinding, we're doing a test shot. It's that if we have an investor visiting, we tried to line that up with test shots, because if they get to push that button and feel that's
a pretty
punch,
good demo.
Yeah, it's oh man, there's nothing like it. So it's great to be able to show people the things you're working on. If you're doing a B2B SaaS company or something, and you're like, oh, look at this cool dashboard that we have, or something. It's like, it's different than if you say, look, here is a giant concrete tunnel, 20 feet by 20 feet, 300 feet long, and inside it is the world's largest gun, and over here is the control system for it, and you can crawl down the barrel if you want, and your hands will get dirty. Like, it's a very different thing to walk next to it and hear the echo of the space around you, and you can see the weld beads and the slag and it's a visceral, physical thing. So if you're considering doing hardware, there are rewards. Even if I don't have as many Git commits as I used to. My GitHub history has a lot of blank spots now. I used to do a lot more software, but there's other rewards.
It definitely is. Yeah, I mean, the flip side of you have to get people to believe is that once you get them over that first initial hump of incredulity, once you get someone to be like, but maybe, and then you can be like, and we're building a space gun, right? Like the thing itself has so much more kind of intrinsic just, I don't know, energy to it. And I mean, in this case, literally, but that it is a little bit easier to get someone excited about it.
Yeah.
But that first step is often very different. Well, it's interesting, actually. This does fit with other examples I can think of, but it is counterintuitive that at least early on, people are not as interested in the technical diligence. But then at a certain point, it's like, that kind of makes sense really early on.
Right. So some of the early investors are basically like, okay, and when you get to space, what are you going to be doing? And we'd say things like, well, look, there are some cool, weird things that this system enables that, first thing is, it's weird in that, a traditional rocket, you get to pick the orbit that you're going into. If you're a customer, you want to go into an orbit, you buy the rocket, it'll put you into that orbit. Our system is going to be, 10 or 15 kilometers long. We can't change the angle. It's pointed where it's pointed. It's going to go into that orbit, which is in some ways a big restriction. But one of the ways we can sort of get over that, what that means is that any customer who wants to put something up in a different orbit, are they shit out of luck? Well, one of the first things we could put up is a whole fleet of space tugs. And we can refuel them for nothing because we have the cheapest access to space there is. So yeah, we'll shoot your satellite up, and then we'll put you on a first-class ticket to whatever orbit you want on a space tug that's not running some dinky ion thruster that's going to take you 6 months to get there. We'll put you chemical all the way, buddy. We'll put you in your orbit in 15 minutes, no problem. And then we'll burn chemical back to that same orbit, and then we'll refuel it because fuel costs nothing to put up for us compared to anybody else.
I gotta be honest, I love, my reaction when you said space tug was like space gun, space tug. You're just taking kind of low tech, real blue collar things and being putting space in front of it.
Right.
And
space tractor.
Yeah, space tractor, right? Yeah, but that is sort of part of the appeal here is you change the economics of it and suddenly you can do just fundamentally different things.
The thing is, we are this whole system is an infrastructure project disguised as an aerospace project. Like the gun system, part of the reason it's so long is so that we can make it out of mild steel. There's no Inconel, there's no titanium. I mean, on the vehicle there might be, but probably not. It'll probably be stainless steel and phenolic resin and carbon fiber. But the infrastructure is mild steel and concrete. We're going to be buying stuff from the pipeline industry. And when you think of like a 15-kilometer long aerospace project, you know, if you use SMAD, I don't know if anyone knows, it's Space Mission Analysis and Design, it's the Bible for aerospace engineers. There are tables in there that will tell you how to scope out every single possible kind of thing you can think of for aerospace. And if you use that book, it's going to tell you, oh yeah, this thing is going to cost you $5 billion to make. But we're throwing that book out. Like we're not buying sensors from Honeywell. Like we're not buying, I'll give an example. The pressure vessels, part of our magic sauce is that we pop burst discs. And we have to pop them with exquisite timing. As the projectile goes by, the burst disc has to pop. And the projectile is traveling at 8 kilometers per second. There's burst discs that release gas into the barrel. There's no valve that opens fast enough. The projectile is traveling 8.5 kilometers per second. If you have a gate valve that's 2 feet in diameter, that's going to take a couple seconds to open. So we need things that open in less than a millisecond, and so that's a very energetic process. And so we have a I can't go into details on exactly how we do it, but I will say that it involves large amounts of electricity. We have a large capacitor bank, and we switch and we dump power very quickly. And we, as part of testing this thing, we had to get that power inside the pressure vessel to get to the burst disc actuator. So we have a giant capacitor bank. It's going to be dumping 100,000 amps at 3.5 kilovolts in 10 microseconds. And we need to somehow get that power from normal air through the wall of a 1/2-inch thick steel pressure vessel, and that feed through that's going to be carrying all that power needs to handle the power, and it needs to survive 1,000 psi pressure on it, and it needs to be super robust and reliable. And so you might think, oh, well, where are you going to get one of those? What's that feed through? What does that feed through look like? If you went to go try and buy one of these, I don't know if it's possible to buy them. We didn't even bother trying because we thought they would be hundreds or thousands of dollars. And instead, we went down to Home Depot and we got a 1-inch diameter NPT fitting, just a threaded fitting, and we put it on a block of wood, drilled a hole, and put a giant piece of copper right through the center of it, and then filled it with epoxy. And we scuffed up the copper a little bit with some sandpaper. And then we took this, it's a NPT fitting with a rod of copper running through surrounded by epoxy. We stuck it in a pressure vessel. We pressurized it to like 1,500 psi to prove that it could handle higher pressure. We did a couple of capacitor discharges through it to make sure that it wouldn't destroy itself. And then we started using them. It was literally $5 in parts and 10 minutes of technician time to build them for a part that would be incomprehensibly expensive if you tried to buy it off the shelf. We got rid of all the ridiculous requirements that other people might have and said, we need this tomorrow, and made it. I don't know. We did that. I can't even say we did that for 100 different things on the prototype.
Yeah. Kind of the classic, you can just do things.
Yeah, totally.
And that's how you make a space gun. I want to end with a question that I've been asking guests here recently, which is, a lot of advice that people give in startups functionally adds up to just like that, like plane survivor meme, right? Like it is sort of just packaged survivor bias.
Yeah.
That sounds good and is like makes it feel good because it makes you feel like, oh, now I have the knowledge and my problem will be solved, and then like it doesn't actually do that.
Right.
Are there things that you have learned though that you think do generalize or like actually are kind of particularly useful, or that you maybe unlearned, right, that have been particularly useful? Especially like you had a longer career working in biotech and aerospace and at various size of companies before you eventually start your own company, and you're in the thick of it now. Are there any things that you think like, most of that is like not real, but this feels like it actually is something that that is true and generalizes and that I can sort of share with people in the audience that might be considering starting hard tech companies?
You have to be willing to commit really hard and work really hard, especially early on. And you have to be willing to get kicked in the teeth, especially if you're on the fundraising side. I mean, I think this is part of the reason to have two people at a company and not be a solo founder, is because if you're a solo founder, you don't have anyone to complain to. You don't have anyone to commiserate with. Like, no one, I mean, I guess maybe here you've got a bunch of other, this is actually probably a fantastic environment, and I wish maybe we had a cohort of other, co-startups to commiserate with. I mean, it's really hard to shoulder the pressures, and especially once you have a few employees, and suddenly here's people who you convinced them to join you on this journey, and now they are dependent on you. And like, if you fail to raise money, they're out of a job. Like, if I miss some technical detail and I've taken us down a wrong track, then our team is SOL, and we're going to die. So I think you have to be able to handle that pressure without burdening the other people at the company with it. Again, maybe if you're founding it, your co-founder, that's a reasonable person where you can commiserate with them, but you can't complain to your employees that like your job is hard, like, or something like that. And people who aren't in the startup scene, and I have a wife, and while she is supportive, like there's a certain amount of like she isn't a startup co-founder. I can lean on her in some ways, but she's not in the thick of it and doesn't have the same pressure. She has different pressures. We have a 3-year-old, so she has all kinds of different other pressures. But it's a different thing. People aren't going to understand what you're doing and what's going on, and it can be lonely, and it can be stressful, and it can be it's not glamorous in a lot of ways. Like, if you're doing it right, I think it's not glamorous, at least not early on, because like there's no glamour to just like staying up until 2 a.m. It's nice to tell the story later. It can feel glamorous to sit on a stage and have all these people, listening, hanging off your every word. But for the first 3 years, when no one gives a crap and you're just slogging away, and most people are saying like, well, your heat shield's going to have to be too thick and it's not going to work. So, what are you doing? Yeah, it's a lot of it isn't fun, and so you really have to believe and have people who believe with you.
And then every once in a while, you get to hit the big red button.
Yes. yeah.
And
yes. And then when you get those, occasionally you get those little moments of victory.
Nato, I very much enjoyed the conversation. Thank you for joining us here tonight and speaking to all the members at SBC.
Thank you.